Over the centuries, astronomers have identified thousands of asteroids in our solar system, also known as minor planets or planetoids. Asteroids are small, airless rocky worlds, leftovers from the formation of our own solar system about 4.5 billion years ago. Like planets, they revolve around the Sun in orbits that sometimes cross paths with other planets. In our past, asteroids have hit Earth. One is even linked to the extinction of dinosaurs. More asteroids will surely collide with Earth in the future. Aside from their daunting potential, asteroids carry with them the key to unlocking the history of our solar system. The asteroid Bennu is classified as a potentially dangerous asteroid coming closer to the Earth with every orbit. NASA's mission Osiris Rex launched in September of 2016, and it's expected to rendezvous with Bennu by 2018. The spacecraft will actually touch the surface of Bennu and collect samples, returning them to Earth. Scientists will then be able to study the composition of Bennu, hoping to understand the mysteries of planet formation, how our solar system evolved, and quite possibly how life itself originated on Earth.
Anytime you're involved with a mission that's sending a spacecraft, off away from the Earth into the solar system to sort of go to a world, or in this case, an asteroid that's never been explored before, it's just sort of a very cool fundamental thing. Sort of goes all the way back to your childhood when you're imagining how great it would be to go out and explore the solar system or the universe. So it sort of brings us back to that stage a little bit emotionally. The target of the Osiris Rex mission is the asteroid Bennu. I actually have a little model of it. It's sort of black as coal. In real life, it's even blacker. It's even darker. It's got a weird shape, sort of an oblate shape. It spins once every about 4 hours, and it's about end to end about 500 meters. So, if you plunk this down in the front range, you wouldn't even notice it. It'd just be a little hill that you would just climb over. But in space, it's a very interesting body, and one of the reasons why we're interested in Bennu is that we can tell from ground-based observation that it's actually a very primitive body, and that the material here has not been altered that much from the formational epoch of the solar system. So we know if we go to this body and take a sample, it's relatively pristine, and it hasn't been changed that much over the last few billion years potentially. The fundamental science of Osiris Rex is really cool, and it actually involves studying the properties and the chemistry and the mineralogy of materials that date back or have a lineage that dates back all the way to the formation of the solar system. Once we get the sample from Osiris Rex, from the asteroid back to Earth, and analyze it, they'll have insight into a lot of the activities, a lot of the basic physics that were going on in the early solar system. That can profoundly change the way we think about how the solar system first came together and how it's evolved over time. The spacecraft is going to spend a couple years orbiting around this body and taking all sorts of measurements and the like. And that's where the University of Colorado team comes in. And we're fundamentally involved in studying the mass distribution of the body. And we do that by measuring its gravity field. It's a microgravity environment, so you would weigh 1/1,000,000th of what you weigh on the Earth. And the way materials behave in these environments are very different.
5, 4, 3, 2, 1. And liftoff of Osiris Rex, its 7-year mission to boldly go to the asteroid Bennu and back.
Any space mission has fundamental challenges from the start, even from launch, because that's, you got this huge rocket, lots of thrust and power. If anything goes wrong, it's the end of the mission. Happily, we had a successful launch. Waiting for that moment when you actually get there and you see what the environment is like is exciting, because you don't really know how well you planned until you actually show up. So once that sample is back on Earth and put into the laboratory, that's where sort of the real science of the mission actually starts. One of the other big results from Osiris Rex will be a clearer picture and a better understanding of what sorts of materials do exist on the surfaces of asteroids. And is it possible to take that material and turn it into something useful in space that could help with exploration? An example would be if we can extract water or some gases or something from this material, you could potentially use that as a propellant. So beyond just the scientific realm, the Osiris Rex mission can also have really a large impact on potentially future use of resources in space, and even future defense of the Earth, what's called Planetary Defense, pushing hazardous asteroids out of the way.
Every time you get in your car, you take a risk that you might have an accident. So what do? You take training, you practice, you go through a certification program. And these are all things that we do in aerospace as well.
While navigation through space can prove very daunting at times, many of the steps are just the same as your GPS takes every time you get in your car. Osiris Rex is a mission to retrieve data from the asteroid Bennu. The first step to successful navigation to Bennu is deciding when to leave.
We find an optimal trajectory, so depending on where you're going to go, you try and find when you would need to leave to get there using the least amount of fuel. That's usually what we worry about the most. For Osiris Rex, it was, I think they had a 28-day window, so that's quite a bit. For other missions, it can be just a few days.
And liftoff of Osiris Rex, its 7-year mission to boldly go to the asteroid Bennu.
A lot of times what you end up doing is you end up visualizing a process of how you get from launch and ascent into the commissioning phase and into the on-orbit operations. The orbit is really determined by what kind of mission, what kind of science data do you want. For manned missions, it's what do you plan to do? Where do you plan to go? What orientation do you need to be? And so there's a lot of thought before you ever put pen to paper. The problem is, as engineers, we have to try to limit our risk as much as we possibly can. You cannot know everything. You cannot engineer everything. You go through and you try to mitigate as many things as you possibly can. But can you do that for everything? Of course not.
One of the difficulties in planning the trajectory of Osiris Rex was the gravity boost from Earth. Gravity boosts use gravity to give the spaceship velocity without using fuel, similar to a longboarder cruising downhill.
Typical design cycle will look for a trajectory first which doesn't use any gravity assist, just to see if we can get there at all. And then they'll try and add in gravity assist from different planets and see if they can still find a trajectory that would use the gravity of a different planet.
The gravity assist is helping to change the direction of the orbit that would otherwise not be possible without using extra fuel. The Osiris Rex mission is utilizing more than just our regular GPS technologies. It's utilizing technologies such as LiDAR and tag cams.
LiDAR is an acronym for light detection and ranging. So it's an instrument that uses lasers, basically, and it shoots a laser bounces the light off of a target, and when the light comes back, it measures how long it took for the light to travel there and back.
This is the technology that allows us to know exactly how far away the spaceship is from objects. The Apollo mission used similar technologies in order to navigate safely to the moon.
Hello, Houston. Sweet 16 has arrived.
Osiris Rex is also utilizing tag cams.
We have a model of whatever we're looking at, say an asteroid, and we have landmarks on the asteroid's surface, so rocks or craters or just features that we can recognize when we take pictures of them. And so as we come around and we take a picture of the asteroid and then we see features that we recognize, that tells us where we are with respect to the asteroid.
Although all of these technologies are helpful, maybe none more than the Deep Space Network.
We use the Deep Space Network, which is a complex of giant radar dishes, 34-meter and 70-meter radar dishes that NASA operates. And that's what we use to talk to spacecraft as they travel through space.
If you have a critical command and you don't want to proceed beyond that point until you know it's functional, then you have to wait for the command response to come back. Two-way light times can be anywhere to nearly instantaneous during the launch and ascent phase to dozens of minutes. If we go to Mars, we go to Saturn, we go to Pluto, or even further out, it can be half an hour, half a day, just depends upon how far away it is. You end up with a situation where you've thought of everything you can possibly think of, and then you launch and life happens and you've got a new problem. The reason why we have humans in the loop is because we have to be able to deal with a situation as it rapidly evolves.
While space navigation is not as accurate as navigation on Earth, with enough pre-mission research and planning, getting to Bennu safely is far from a pipe dream.
It may not look like much, but this is the first close-up image of Mars, taken by the Mariner 4 spacecraft in 1965. 50 years later, the first images of Pluto, sent by the New Horizons spacecraft, a spectacular contrast. But this is the image that says it all. The New Horizons team, reacting to the first photos of Pluto. A moment played out dozens of times in other missions, always starting with tense anticipation.
There is a certain tension, and when we see those first images, it's the excitement in the air is pretty awesome.
Imaging systems have come a long way since Mariner 4, and space missions are becoming more daring. Missions with highly tailored requirements to investigate the planets, asteroids, and comets, all with their own custom-made cameras using the most innovative technology. In fact, a NASA engineer at the Jet Propulsion Laboratory developed the first digital camera back in the 1960s. Over the decades, the cameras became easier to build, the parts got smaller, and image sensors designed to withstand harsh environments in space. This same technology, developed for NASA spacecrafts, can be found in our cell phone cameras, not to mention applications in the medical, automotive, and surveillance industries. The images they take are nothing more than milestones in photography. They call to our collective sense of wonder, and they fuel the public's interest for space exploration. Like this one of Victoria Crater on Mars, taken by the High-Resolution Imaging Science Experiment Camera, also known as HiRise, sent to the Red Planet aboard the Mars Reconnaissance Orbiter. HiRise is the largest camera to ever photograph another planet in the solar system, with a telescopic lens that produces images in unprecedented detail. It's firmware developed by Renee Mize, Mission Assurance Manager for Ball Aerospace in Boulder.
As we look to the future and we think about human exploration of Mars, think the Martian, right? HiRise is going to be invaluable in looking for some of those landing spots and where can we put up colonies.
We're meant to recon like the military.
Jim Bergstrom is a system engineer for the HiRise camera, which he says was designed with two main requirements.
Number one, look for hazards on the surface, boulders, ravines, whatever, steep slopes, anything that would prevent a robotic lander from safely landing there.
At an altitude of nearly 250 miles, HiRise can take pictures that show objects the size of a basketball. and it can take stereo images that show depth and angles.
So that's number one. Number two is support science. And the theme of the mission at the time, the Mars program even, was follow the water.
Where there's liquid water, there may be life.
We think we've seen moving water. So all evidence is that it is a live planet, right? And it's just pretty awesome.
Taken by the HiRise camera, these dark streaks, abundant on the steep slopes of ancient bedrock that would appear to come and go over time, a phenomenon scientists call recurring slope lineae, or RSL.
The best analysis, I believe, from the science folks is that there is highly salty water, very high concentration of salt, brine, that melts a little bit. It doesn't flow on the surface, but it wets the soil, so it looks darker, and then it goes away. Now, it's possible there are other explanations. That's why you got to go to the ground to find out for sure. But that's probably the most significant finding from the HiRise camera on the science side.
Not far from Mars, the asteroid Bennu orbits the Sun. Its journey began around the time the Sun formed, about 4.5 billion years ago. In that time, scientists think Bennu changed very little, a sort of time capsule that may contain the building blocks of our solar system. One of the major challenges to the Osiris Rex mission is to collect a sample of Bennu and return it to Earth. Naturally, the mission would need cameras, specifically designed to help get the sample. In fact, Osiris Rex carries 3 cameras, a wide-angle camera called the SamCam, used to document the actual sampling event. On the other extreme is the Polycam. That's basically a telescope with a 600mm focal length, similar to the ones used by sports photographers. And then there's the MapCam, which will be used to map the whole asteroid.
Together, they have about the functionality and resolution of a lookout on one of those tall sailing ships back in the 19th century that would sit in the crow's nest with a spyglass and tell the crew and the captain what was coming, what they could see. That's basically the function of this camera suite to the mission.
It took a team of about 100 people to develop the cameras. Half of them were from the University of Arizona.
So this team is the same team that built a number of cameras for Mars missions, for other missions to Titan, and a number of other camera missions. On a mission like this, where the cameras are very important, they're the eyes of the satellite.
The MapCam is the second smallest camera in the suite. Not only will it map the entire asteroid, but Dobany says the MapCam will also be used to find possible natural satellites.
At this point, there's no natural satellites that are known or that are expected, but if there was, it would change the way the Osiris Rex has to orbit the asteroid, and so it's a major thing that we have to look for just in case it's there, even though it's not anticipated.
Although each of the 3 cameras is given a specific task, each camera is functionally redundant.
So for example, if the MapCam was to fail and one of its responsibilities is to look for those natural satellites, well, the Polycam has a smaller field of view, but it's also more sensitive, so you could do that same satellite search, you just have to do it from farther away. Obviously hoping that all 3 cameras, go through launch and turn on, and that they're all working perfectly by the time we get to Bennu. But if one of them was to fail, the other 2 could be used to make up for it by adjusting the way we fly the mission.
It's a lot harder than you might think to design a camera that has to go into space.
For one thing, space is a vacuum, and the wavelength of light is slightly different than the light observed in Earth's atmosphere.
All that means is it changes slightly the speed at which the light is traveling through the medium. So you have to design for that.
Another challenge, designing a camera that operates at temperature extremes, from very cold to very hot. These differences can be modeled in computer simulations. However, sometimes these models can get very complicated.
So you try to keep everything as simple as possible, yet accurately reflect what you're trying to describe. So it's a little bit of a trick, it's a little bit of an art, but we get there in the end. Mostly what you do is you test, And you try to think of situations that you're going to encounter and duplicate them in the lab and then test for them.
Risk and his team will continue to monitor the health of the cameras as they continue their journey to Bennu. They'll also get to play a role in deciding where Osiris Rex will take a sample.
So it's exciting to be part of the mission because, and frankly, there's a lot of exciting things about this mission. But I would say one of the most exciting is the feeling of surprise and not knowing what's going to happen. Because a lot of the information that we need to gather the sample off the surface of the asteroid, we don't have yet. We have to go there and get it. And a lot of that information is visual.
They may be similar to other cameras, but space cameras are tougher and a lot more sensitive. They must be able to travel billions of miles, withstand radiation and thermal fluctuations. They need to be lightweight and use little power. It may even take longer to develop the camera than the actual mission length. But once they start snapping pictures, these cameras take us a cosmic step forward in our understanding of the universe. And these cameras stand as among the top engineering achievements in space exploration.
Oh, I think it's awesome. I mean, when you take a look at all the exciting pictures we're getting down and how we can contribute to science today and in the future, you know, there's a sense of pride, accomplishment, and just awe. And I can't wait when my grandkids are a little bit older and I can pull up some of these pictures and say, hey, look what Grandma did, you know, so ain't it cool? So.
CU Boulder is one of several universities nationwide that's partnered with NASA on the Osiris Rex mission. CU Boulder professor Dan Shearers is a principal investigator on this project, and he has several graduate students working on his team. We talked with one PhD candidate to hear about her experience working on the project.
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of Osiris Rex.
I remember when I went to the launch recently.
Boldly go to the asteroid Bennu and back.
I know as a graduate student, you're usually working on something pretty focused, so it was pretty awesome to be there and kind of see the bigger picture. It was like a good reminder, like, you know, even though we're doing this small little part of the science mission, there's a bunch of people who are doing small little parts of the science mission, and somehow like having 100 people or something, all each working on their small little part somehow creates this big project, right? This big thing that's gonna go to an asteroid and, you know, find a lot of science and do a lot of cool stuff. So it does feel really special to be part of that.
Solid rocket booster jettison.
Separation looks good.
What I work on is looking at natural satellites around Bennu, and Bennu is the asteroid that Osiris Rex is going to. All natural satellites they're like these little mini moons, kind of objects that could be in orbit around Bennu, and they're kind of like rocks or boulders or even just little pebbles. We know that nothing larger than 15 meters exists there. Because of the imaging that we've done on Earth with radar. But we don't know anything smaller than that. So anything smaller than 15 meters could be in orbit around there. So my job is kind of to figure out if there are objects that could be, say, the size of a basketball, you know, where would they be in orbit and how long can they stay stable in certain orbits around Bennu? If they are in orbit around there, are they in the same orbits that possibly Osiris Rex will be in? And if there's issues with the possibility of intersecting paths. And if they do, that could be a huge issue, because if you have something the size of a basketball hitting your spacecraft, that could be end the mission. It's the first kind of spacecraft mission I've ever been part of, and it's got like a little bit more of an emotional feel to it than I guess, you know, your average, you know, getting your average tweet on some other spacecraft mission. You know, this one's like my baby, right? So it definitely does feel like I have an impact on it, and I think that's really cool. You know, not everybody cares about what's going on with NASA or space. You know, there's other things to worry about in life. But I think it's really cool when people are inspired by Osiris Rex. So maybe it's not necessarily about the science, but you know, somewhere some 8-year-old kid will be super excited about this and be like, I want to go to an asteroid. And I think part of the success will be getting people interested and kind of learning a little bit more about NASA and asteroids and space and stuff like that.
The Osiris Rex spacecraft will touch the surface of Bennu using a device called TAG-SAM, short for Touch and Go Sample Acquisition Method. The TAG-SAM will shoot a burst of gas, stirring up loose materials, and collect them in a sampler head. The samples will then be sent back to Earth for detailed study. Jim Harris, a researcher with Lockheed Martin, developed this idea many years ago in his driveway, using just a shop vac and a plastic cup.
So I took a plastic cup, put some holes in the side of it, and put an air hose to it, and cut a hole in a large E-size sheet of paper, and took it out in the driveway, and we basically fired the gas into the surface and to see how much would go through the holes in the cup, and whether or not the material that we gathered on the piece of paper would be in the neighborhood of the quantity we were looking for to be able to collect from an asteroid. And it was. So we said, okay, well, let's look at this a little more. My name's Jim Harris. I am the TAG-SAM lead for the Osiris Rex program. So this is the sampler head that will collect the samples from the surface. There's a gas line, there's gas bottles that are on the arm, and there's a flexible gas line that comes down through this hole, feeds into these two tubes here. There's a tube inside here that goes down to this surface here, and then the gas is injected here into the surface while the sampler head is on the surface. So that gas being injected into this area then stimulates all the material, dust and loose rocks. This is a filter, basically just a screen, so the gas transports the material to the vacuum of space, and the screen collects the material as the gas flows through the screen.
What we wanted to do is to come up with a way that you could quickly and efficiently and in the simplest fashion possible collect loose material on the surface of a small body. And that first involved a study as to whether or not it was better to land and spend an extended period of time on the surface of a small body, or to contact it and leave quickly, which is the touch and go, or TAG. And after examining both scenarios, the TAG approach came out on top for a number of reasons, but just logistically, the gravity of a small body is very, very small as well, and it's hard to keep yourself on the surface. You don't so much land as you kind of bounce off the surface, and so if you want to stay on the surface, you have to actively control yourself on the surface. So it's easier just to do the TAG anyway. And so we came up with a sample collection technique that worked in just a few seconds, didn't require any moving parts, and is very efficient at collecting loose material. And this technique that we've developed for TAG-SAM is applicable for small bodies across the solar system, but it could also work in a more traditional landed environment as well. So we could use it at the moon, or we could use it at Mars, or any other of the surfaces that we may explore in the future.
It's very rewarding, especially to have worked on a program like this where, contributing to helping. I mean, people all across the country have helped contribute to the spacecraft and the total mission. And to be part of that and to help further our knowledge of our solar system is very rewarding, very.
Beautiful, beautiful. Isn't that something? I'm nervous for flight out here.
The surgeon says everything looks fine.
Space travel can be hazardous. Astronauts are constantly bombarded by cosmic rays, high-energy radiation that comes from mostly outside the solar system. On a trip to Mars, cosmic rays can easily pass through the spacecraft, exposing astronauts to a dose of radiation that would raise their risk of getting cancer. Unless the spacecraft is properly shielded, but launched from Earth, shields are heavy and require more power to lift them into space. But what if the astronauts could rendezvous with an asteroid and convert it into a spacecraft? A daring and innovative idea that's already on the drawing board.
August 7th, 1972. An enormous solar flare erupts from the sun, pumping dangerous energetic particles towards Earth.
What a ride, what a ride.
If the flare happened 5 months earlier, the crew of Apollo 16 returning from the journey to the moon would surely have perished. These were the early days of spaceflight.
Man, we come a long way. Hey, John, it's easier to go straight across. That was fun.
Researchers were just beginning to understand the effects of cosmic radiation on humans.
Tony, how about an extension, you guys? We feeling good.
X-rays and gamma rays from the sun and galactic cosmic rays, high-speed and electrically charged particles can penetrate spacecraft from every direction and pass through the skin of astronauts, leaving behind damaged cells or DNA.
All right, we think you could just about head south now.
Wow, what a place. What a view, isn't it, John?
Over time, this constant bombardment can lead to serious health issues and sometimes even death. For astronauts on interplanetary journeys, like going to Mars, radiation shielding will become crucial. The sheer bulk of shielding that is used to protect the astronauts will be expensive, since it will take more fuel to launch it into space. Instead of creating a better shield, why not just hitch a ride inside an asteroid?
In a lot of ways, asteroids themselves could be sort of, pre-made spaceships for us out there in the solar system. Rather than launching materials off of the surface of the Earth, and with all the expense that entails, getting outside of Earth's deep gravity well, being able to use a already existing structure out there like a small asteroid it makes sort of economic sense, and it makes physical sense as well.
These ideas are getting serious attention from NASA, but to get the asteroid to go where you want it to will be a challenge. It's not as easy as attaching rocket engines to its surface.
The biggest obstacle is the mass. So even though asteroids are small in a cosmic sense, they're still rather heavy, and much heavier than any spaceship or spacecraft or satellite we've ever made. So you need a lot of propulsion to really make much of an impact.
With funding from NASA's Innovative Advanced Concept Program, Made in Space intends to turn asteroids into fully autonomous spacecrafts.
I think their plan is to go to an asteroid and basically just pick up chunks of the asteroid and throw them off. It's just equal and opposite reactions. So you throw mass off this way, it moves your asteroid this way.
Companies working on this technology hope to have more opportunities to interact with asteroids, and that's where the Osiris Rex mission can be so useful.
The first time we're really going to touch down and touch the surface of a small asteroid, like the near-Earth asteroids that are easy for us to get to. So we're going to start to learn something about the material structure. Then of course we actually get the sample back so we can see what it's made of.
The actual material of the asteroid itself could be used as a resource. Many asteroids have a lot of water in them. Not necessarily water the way a comet, just existing water ice, but water, what we call water of hydration. It's water molecules or fragments of water molecules that are bound into the mineral structure itself. And all you need to do is heat that rock, bake the rock basically, to get the water to come out. And many asteroids we know are some of them are up to 20% by weight water. And that's a great resource for, human life support, for water to drink, but you could also, use that water, splitting it apart into its constituent hydrogen and oxygen to use for rocket fuel as well.
So I think, there's progress being made on all these fronts, and, if people keep putting effort into it, then will have the capabilities to, to do the basic parts we need in the near future.
A future that may be dependent on the raw material that is out there. The reality of turning an asteroid into a spaceship is closer than ever.
There's been this concept of world ships for a while in science fiction, where you could, maybe hollow out the structure of the asteroid and actually, live inside the asteroid itself.
It is possible to create a spaceship out of the materials we can find on asteroids. It would just have to take careful planning and engineering to make it a reality.
It's well within the capabilities of the up-and-coming commercial companies, especially like SpaceX, who are already planning on being able to go to Mars. Going to an asteroid becomes that much more simple. And so I think it's well within our capabilities to go and do that, and I think it's inevitable that we will.
Asteroid spaceships offer a creative and innovative way of maintaining human life in outer space. However, an intriguing possibility exists that asteroids may have already been maintaining and transporting life for millennia. Scientists would be fascinated to find evidence of life on an asteroid, life that's remained dormant until a more suitable habitat presents itself.
So panspermia is, the Greek word pan is all or every, and spermia is basically its seed. And the idea is that life formed relatively early in the formation of the universe, and that it's thus kind of abundant, and it's passed through the universe by way of meteoroids and asteroids and comets and those things. A specific example for Earth would be that there has been some evidence that researchers point to in which if you take one of the origin theories of life, which is that it was the formation of RNA, which we know is one of the important processes in the central dogma of life for biology here, that early Mars was actually more suitable due to the presence of boron and some other things, that it's actually more suitable that RNA would have developed there as opposed to early Earth, because early Mars actually had some features that made it more likely to form life. And so if that's the case, we also have evidence that we do know of meteoroids that were sort of planetary fragments. An impact event happened on Mars, sent fragments to Earth, and we have evidence of that, geologic evidence that that's happened. And so the idea is that, well, maybe if life started on Mars, it would have hitched a ride on one of these fragments, and then that's how life started on Earth. So existence is an interesting idea because you really have to ask, what would life be doing? There are several components to what involves a life cycle, for instance. There's the ability to sort of grow, there's the ability to reproduce, but then there's also sort of just a maintenance state or a dormancy. And we do have evidence of certain microbes that are able to remain dormant when they encounter a very harsh environment, physical environment, where there's maybe no water, there's no nutrients. They can sort of go into this survival state in a relatable term, maybe the way that certain animals hibernate over the winter, right? They're not really doing much. Their metabolic rate goes very, very low, but it's just enough to keep them sort of alive so they don't perish, but they're not doing anything. And so part of what this mission to the asteroid is to look at, in addition to all the geological features, is they're going to try and take samples after about a year of orbiting, collecting all this data. They're going to try and take some samples and bring them back. And from that, they're going to evaluate, most likely, if they could potentially revive something that's living there. Of course, we've never found this. Life has never been found outside of Earth. And that's something to keep in mind, because we base all of what we know about life on what we see here on Earth. If you kind of follow back the origins of life, we all have one ancestor. Essentially, that's the accepted hypothesis right now. It's called the last universal common ancestor, or LUCA. And that gave rise to bacteria and archaea and eukaryotes, of which humans are eukarya. So it's possible that life is actually in a dormant state on one of these asteroids or meteoroids or comets. It's likely that it's too harsh of an environment for them actually to really be active, right? In other words, to be self-replicating and reproducing. And so you would think, again, that if they came to life, or life was generated somewhere, it would be on a bigger object like a planet or a moon.
maybe as we increase our missions to Mars, we will find some subsurface life. We know right now that it's unlikely surface life exists because of the radiation environment and some other things. But the reason why these missions to Mars, as well as the asteroid and potentially Europa and some other places are so important is because there's so many things we just don't know about those locations. And we might find life, but we might not. We might eventually find that there is no life in our solar system and we have to go to other solar systems. So same thing I would say with these sort of unifying principles of physics. Who's to say? The original and probably the most famous evaluation of this was the Drake equation, which was, Frank Drake was an astronomer at Cornell and was involved in the early astrobiology discussions with people like Carl Sagan. And in his formulation, depending on how you change the parameters, there can be anywhere from maybe we're the only place or there's 156 million potential locations that host life. In that time since, there's been many other astronomers who have also tackled this question, and one of the most recent ones, again, projected somewhere in the probably hundreds of millions range in terms of places or locations in the universe that are capable of supporting life. So I would think that it would be actually more unlikely that we're the only place that life exists, and much more likely that it exists elsewhere in the universe.
Resources on Earth are limited. Some are very scarce. Asteroids might turn out to be precious blocks of metal floating through space. Some may even carry water and other elements useful in the exploration further and further into space.
Resources have become not just an element of survival, but what sustains our civilization. And we are in this insatiable quest for them because they're so useful to us. So in a way, we're going to space, yes, to explore, yes, to learn, but we have to also look at it from the point of view of integrating space into our economy. How those materials, how those resources can be useful to us as we expand our civilization into space.
Space shuttle now on internal power.
Well, asteroid mining, as is Earth mining, it's an activity that focuses on extracting valuable resources that we can utilize in multiple applications.
7, 6, 5.
Now, when I talk about having valuable resources that can be utilized from asteroids, we are talking about the same type of materials that we humans consider as valuable, either for our own survival or as essential to our civilization, to our high-tech, industrialized society. And so the type of elements that we use, for example, metals that we use for everything from cars to phones to buildings, like iron, nickel, cobalt, platinum, gold, those things are also contained in asteroids. And that's why we first thought about, well, maybe we can use them for our own needs, just like we have done here on Earth. Well, it's a little bit expensive, it will take a few years. What else can be used for? Well, we can be useful for us to start extending our civilization. We can now probably stay on the moon for more than a few days. We can stay for weeks, and we can use the resources for that. And so the way I look at asteroids is that they're going to be either useful for allowing us to keep traveling further and further and to allow us to live longer in the moon and Mars, or at some point to bring it back to Earth. And so now you start thinking about asteroids as the equivalent, as the terrestrial equivalent, or as the celestial equivalent to those gas stations or those convenience stores that can be used to obtain the material that you use for not just sending humans, but rockets into space. And so what you're seeing in the last 40 years or so is the emergence of companies that are going after asteroid mining, And they have changed their intentions. They started looking at platinum and gold and all those things, but they soon realized that that was not the business case. They soon realized that if they go after the water and they can sell that to governments or to private companies that are going to space for other reasons, like space tourism or for communications or satellites, then they're seeing this as a business. This happens to be the first American mission that will have a return a sample from an asteroid. So anything we learn, anything that we can test will be invaluable. I mean, will be priceless in terms of designing the next missions for asteroid mining. So Osiris Rex is contributing significantly to the field of asteroid mining.
2, 1. And liftoff of Osiris Rex, its 7-year mission to boldly go to the asteroid Bennu and back.
Time and space reduce us to microbes, going on about our lives. The space program gives us proof that when we work together, no project is too big. And when we work together, dreams really do become a reality.